thank you for joining in and being a part of this evening. This is Shruti Kurana on behalf of TCS Ion. I welcome you all to this masterclass where we will talk about analog custom IC. In today's rapidly evolving tech landscape, the demand for compact, powerful, and energy efficient devices is at an all time high. Powering this innovation is VLSI, very large scale integration, the technology behind modern system on chip design. This exclusive masterclass will walk you through the complete spectrum of VLSI chip design, helping you understand how these advanced chips are built and what makes them so critical across sectors like mobile, healthcare, and industrial IoT, etc. The key highlight of the session includes fundamentals of analog IC design, core concept involved in analog IC design and analog design flow. Whether you are a beginner exploring the field or someone looking to build a strong foundation, this masterclass will equip you with the essential knowledge to navigate the world of semiconductor design. We are honored to welcome Professor Abhishek Kumar and Professor Kapil Janwal from IIT Hyderabad, who will be leading this insightful masterclass with their deep expertise and experience. They will warmly guide you through the fundamental of VLSI chip design, touching upon analog and custom ICs and help you connect theory with real-world applications. So let me introduce them. Dr. Abhishek Kumar is an assistant professor in the Department of Electrical Engineering at Indian Institute of Technology, Hyderabad. His research focuses on analog radio frequency integrated circuit design, full duplex wireless communication, and wideband frequency synthesis. And Dr. Kapil is an assistant professor in the Department of Electrical Engineering at IIT Hyderabad. His research focuses on analog and digital IC design, CMOS image sensors, 2D, 3D vision sensors, LIDAR, and event-based cameras. A very warm welcome, both of you, sir.
Thank you very much. Good evening.
So, Abhishek sir, before we dive into the core of today's masterclass, I would like to ask you a question that could you help us understand the specialization in electronics and semiconductor world? And where does VLSI stand as per importance and relevance today? What is the relevance also for analog IC design in the current context?
Thank you very much. Good evening, everyone. So if we talk about electronics and semiconductors, so a person right now can specialize in various fields. For example, if they like digital IC design, you can be a digital IC designer. If you like analog IC design, you can go into the analog field as an IC designer. You can also work on the layout side. So where there are specific roles just for doing very special kind of analog and RF layouts. Then there are roles meant for verification. There are roles meant for testing of all these complex ICs. So in that way, I can say that if someone wants, they still have a lot of choices in the area of semiconductors. In addition to all this design, also there is the scope for semiconductor device fabrication. There are roles there also present. Although right now, mostly related to the VLSI chip design, these are the kind of specializations I can think of. In addition to that, if we try to understand the relevance of VLSI in the current context, so all of us already know that these electronic chips are almost present in every gadget around us. So the applications are just increasing day by day. So, and I can only say that, okay, the relevance of VLSI is going to just increase exponentially as time moves on. Thank you.
Great. Kapil sir, would you like to add in this?
An insight to that, if I would like to add. So, okay, so semiconductor industry is something which is not needed to introduce. We all know what is the meaning of chip, where exactly what is the relevance of electronics in our life. Not only you people can, with the knowledge of chip design, you will be able to build something which is not only being used in commercial purpose, but also in defense purpose, medical purposes, space, uh, automation and all, and also the latest field called AI. So everywhere if the compute is there, some kind of signal conditioning is there. So you need electronics, and if the electronics needed to be smart, it comes in the form of a chip, right? So of course, this is very important in the current scenario, whether it is warfare, whether it is security or automation space. Yeah, electronics is everywhere. So it will be helpful. And on the other way, for the business point of view, if you are good, then you can make your own startups also. That is a booming field. So this is what from my side, I guess. Thank you.
Thank you so much. Both of you beautifully explained how VLSI chip design, with its mix of digital basics, analog circuits, and custom ICs, is at the heart of the electronic device we use every day. It's also inspiring to hear that this field is becoming more inclusive with opportunities opening up for students from a wide range of disciplines, not just core electronics. With that encouraging note, it's time to explore the subject in greater depth. Over to you, Abhishek sir. Please take us through the masterclass. Arun is asking, is it possible to apply for AI, ML, and VLSI design? Sir, any one of you would like to take this question? That is it possible to apply AI, ML, and VLSI design? Kapil sir.
Okay. So hi. So basically, when you are asking for AI and ML, so all this computation is being done by, it means your compute power is based on your electronics only. So a lot of computation is happening. So over there in the when you are doing some AI processing, the big hardware is behind, which is doing all this compute. So it is not only algorithm, but it is also that how much hardware power you are having, and those are basically chips at backside, right? So if you can write software, but eventually the compute is going to happen at hardware only. So this is one way that what is the importance of chips, or you can say VLSI in the field of AI. On the other context, if you are asking me that how AI is being used to make the digital hardware, so that is also true. People are using that, but specifically when we are talking about analog, a lot of still a lot of challenges are there, which is still you can say a distant aim as of now. Some of the approaches are being means we do have some you can say means available in AI which are being used to design ICs, but as far as reliability is concerned, and specifically in analog side, still AI is not that much being used as compared to digital. So both sides are there. For AI, hardware is required, and hardware is also sorry, AI is also being used in chip design,
Great, great.
specifically in digital side as of now.
Mhm.
Hmm. So I hope my screen is visible to all of you.
Yes, absolutely, sir.
Okay, sorry for the delay.
It's okay.
So good evening, everyone. So today we are going to learn basics of the fundamentals analog IC design, and along with me, Professor Kapil is also present. So first, I will just give you a brief idea about what is analog circuits, and then after that, Professor Kapil will take over. Okay. So to start the talk, I will just show you is some example of an electronic system. Okay. And I'm assuming many of you might have already guessed what I'm showing. So on the top side, you see that this is a part of a very popular mobile phone, which all of you might be already knowing. And this part is called as motherboard. Okay. So these kind of motherboards are going to be present in almost all kind of electronic systems. And you can already see this motherboard is very dense. Okay, so here you can see there is one very big block, which is also called as a application processor. So inside this, you have an IC, and the overall package looks like this. Then you also have other ICs present. Okay, a lot of ICs are present on this motherboard. In addition to that, you can see these small components, which are actually passive devices, which are needed definitely for the overall system to work. So this is just a simple example, I would say, which you will be finding in it, which actually shows the level of integration which is present in modern electronic systems. If we go a little bit detail into the kind of a motherboard which we are looking at, so on the top side you are seeing this big application processor, but if you go on the other side, you again see this kind of layout. Okay, this is the same motherboard, but we are looking at the back side. So just behind this big digital application processor, which is predominantly digital in nature, you see there is this big IC. Okay, this is also actually predominantly digital, and it is actually providing the memory for the processing. But to support this kind of processing, you also need analog ICs. For example, on the bottom left side, you see there is a power management IC. Okay, this IC will be used to regulate the supply and process the power coming from the battery. Then you also have one IC on the top right side, which actually you will find that it is helping you in amplifying the signal to drive the speakers in the mobile phone. Then you have a big IC here, which also has a lot of analog and high frequency modules. And this is helping you with the Wi-Fi and Bluetooth connectivity. So just taking it one step further, here I am showing you another circuit board, which is also present in most of the modern mobile phones. And here you can see that most of the ICs which I'm showing are going to be predominantly analog or RF in nature. Okay, so just to give you an idea, so here you can see this is a front-end module which is going to contain some high frequency amplifiers, switches. Then there is another front-end module. We have so many front-end modules, so just to support various bands for communication. Since we are talking about a mobile phone as an example here, so most of these analog ICs you can see are going to support the communication aspect. Okay. Then you have some bigger ICs which have analog as well as some digital blocks all put together, and so on. So I wanted to show you this example just to give you an idea that nowadays you want digital processing. In addition to that, we have to have these analog blocks because we are present in this world which has almost all the signals which are analog in nature. Okay. So what I will do is I will share a blank slide here, and briefly I will just tell you what is analog, why do we need analog, and then later on you will get an idea about how does analog IC fits into this space. So all of you will already be knowing this part that okay. So the physical world in which we are living in, it generates all the signals. The signal can be in the form of the sound waves which I am generating, okay, which will travel from one place to another in the form of pressure waves. You can have temperature as a signal. Let's say you want to measure temperature of your room, monitor it, let's say over the time of an entire day or a week. Then we can talk about light itself as a signal. because when we are capturing the image, effectively the light which is scattered and reflected by the environment is containing the information, and so on. Okay, so these electromagnetic waves which are enabling your radio communication. Okay, all these things, if we see, all these signals are analog in nature. Analog in nature in the sense that they're always present. Okay, whenever we are measuring at all the times, and all of their values have valid meaning. And once these signals are present, which are all analog in nature, and you are trying to design an electronic system, you'll find that this electronic system has to have a way to process these analog signals. Okay. Now, how do we process these analog signals? You have to first bring these signals into inside the system. Okay, so we start with these analog electronic systems. It means whatever may be the physical quantities here have to be converted into electrical quantities. Okay, so what do you need? You need some kind of sensors. So I will show this interface and say that these are your sensors which are converting these analog signals which are present in the real world into electrical domain. Okay, now this is fine. So what do we do once the signal is already present in the electrical domain or converted into the electrical domain? We need to do some kind of conditioning or some kind of processing. Okay, so this conditioning or processing, you will find that is predominantly digital in nature. Okay, so what we do digital processing. The reason being because of the advancement of this IC design and VLSI technologies, the digital processing has become very cheap. Okay, it has become cheap and very efficient. So whenever you want to do any kind of processing, you want to somehow convert the signal into a digital domain and do this processing. So just sensors may not be sufficient. You need to add another part here, which will do analog to digital conversion. So I hope now this picture is clear to all of you. You take signals from the world, and all the signals are physical quantities are analog in nature. You convert into electrical domain using sensors. Then this electrical signals, which are again analog in nature, needs to be digitized. Okay, and for to be able to process all the signals and to be able to convert into digital domain, you need to do the IC, the signal processing in analog domain. So the ICs which are going to do this processing have to be predominantly analog in nature. Okay. And if we go to the other side where we have, let's say, done the processing, and this processing was all done in the digital domain, the signal needs to again brought out to the physical world. So what do we need? We need to convert these digital signals into analog signals. So you need what is called as digital to analog converters. Okay. And once the signals have been converted into the analog domain, then we need to drive some transducers. It can be a speaker, for example. Okay. Transducers are going to convert this electrical signals into some other physical quantities. So in general, we can call them as actuators. So to be able to even drive these actuators, you need to do all the processing in the analog domain. And this interface block is also going to have a lot of analog and mixed signal blocks. So after doing this processing. So this actuators can be in the form of your speaker. Already we all know about it. It can be in the form of antennas, which can convert the electrical signals into electromagnetic waves. Even the display which we are seeing. Okay, so the display itself can need to be driven with some analog circuitry, so that finally you can see the visualization of entire output. Okay. Now what I will do is, so right now this is a very basics about where this analog circuitry fits in to this overall electronic system. Instead of actually drawing what is a digital signal and what is analog signal, what I will do is I will share just a quick demo of a very simple circuit. Okay, and based on that, I hope all of you will be able to appreciate our digital circuits are not very different from the analog circuits, but the way we represent the signaling and the way we do the processing can be quite different. Okay, so let me just change my screen. So I hope my screen is visible to all of you. So here I am showing you a very simple circuit. Okay. So here you can see there is a simple circuit which has two transistors. I hope many of you can recognize this basic circuit. They are called as transistor NMOS and PMOS FETs. And when you connect these transistors in this arrangement, and we connect both the gates to an input and take the output at the drain side, this is also called a simple inverter. Okay, ignoring this big resistance in between. So this is a simple circuit where we want to drive this inverter with some input signal, and we want to see how the output looks like. So I have added this extra resistance here, which is fine if it is not clear to all of you, but this is needed when you want to, let's say, add some kind of biasing to a circuit. And I will show you that the simple circuit can actually also act like analog block in addition to doing the standard digital processing. So let's try to apply a signal, which is a very small 20 millivolts swing at the input side. And the signal is at a frequency of 1 megahertz. Okay. So that signal has been applied, and let's see what happens at the output. Here, this simple inverter circuit is being driven at with a supply of 1.2 volts. Okay. So on the right side, you see the input waveform, this V in voltage, as well as the output waveform V out. Okay. So what this circuit is doing is it takes a very small swing input voltage. Here it's only 20 millivolts amplitude, but this transistor action is able to convert this power from the battery. The battery is here, this 1.2 volt battery, able to convert power from this battery, and this battery is, and this battery is power is converted and then used to amplify the input signal. So here you see the output power is or output signal amplitude is much higher than the input amplitude. So this simple circuit is acting like a voltage amplifier. And when we say it's an analog block, here you need to carefully see the value of the signal at all the times. Here you see it's a specific periodic sinusoidal waveform where the value of the signal is important at all the time instants. And also you can see that these values are changing smoothly over time. Okay, there are no some sudden jumps. This is the kind of signals we will be seeing in real life. It may not be always sinusoid. It can be some other random signals, but it will be valid at all the times, as well as they will be having these values which will change smoothly. Okay. Now let's do a simple experiment where I will just change the circuit. Okay. And instead of driving with the analog kind of signal to see the analog output, now I'm going to drive it with a digital signal. Okay, digital means signal where I don't care about its value at all the times. Okay, its value is going to be relevant only at specific time instants. And so here we can see that when we apply an input, okay, this input is varying between two voltage levels, which is 300 millivolt, and here it is a 900 millivolt. So we don't care about its value in between. Okay, so we start from 300 millivolt and then it goes to 900 millivolt. In between, there is a transition, but we only register this value as some high, logic high, and this value as some logic low. Its actual value is also not very important as long as it is within some range. And we can decide to register these inputs only at some specific time instance. Okay, so at other time instance, we can ignore its value. So this is called a digital abstraction. So when we are having this kind of digital signals, what we can do, we can design circuits which will process these digital signals with the help of very simple switches. Okay, so for example, in this case, this NMOS and PMOS are actually acting like switches. And what these switches will do is they can buffer these digital signals to an output. In addition to that, here we also do inversion. So we increase the swing of the input to a higher swing. So here you can see now the swing is increased, and now we are going from close to 0 volts to close to 1.1 volts. Okay, and it is also doing the inversion operation. So the same kind of digital circuit, which actually is designed for digital processing, can be tweaked to be used for voltage amplification. Okay, so the whole point is we are having access to this CMOS technology, which is designed to advance digital processing. But at the same time, we also have requirement of analog processing. So you have to take the signal from the microphone, do the conditioning, then you digitize for further processing. Again, you take the output and you amplify and drive a speaker. So you have this analog blocks which are always required, but they have to be also miniaturized in the form of an IC. And those ICs are predominantly designed for digital processing. Okay, so these transistors are designed to be acting like very good switches. And we have to make sure our circuit, our analog circuit also functions while sitting on the same technology which is meant for digital processing. So this was a very quick example of what we are going to see. Actually, again, so more details you will be seeing in the course. But I hope all of you have got this idea that that digital and analog signals are very different in terms of representation. But when it comes to the IC level miniaturization, we have to design analog circuits using the technology which is optimized for digital circuits. Okay. So
Absolutely, sir.
I will stop here now, and I will hand over the session now, and the later part, Professor Kapil will take over.
Sir, before this, I would like to take one question, which is of Karthik. He's asking that which software you are using for this.
Okay, yes. So right now I am using say Virtuoso Flow in Cadence software, and during the course, so once you will be able to come to the campus, you will be able to allow this access so that all of you can learn. Okay, so this is a proprietary software. Whereas, let's say you want to try out the circuits which will be giving as assignments, those circuits you can always try using NG-Spice or LT-Spice based flow. So, but it will be really good if you guys will get time and then can come for the boot camp where you can do the hands-on directly on this proprietary ADA software. So this is Virtuoso from Cadence.
And based on this, Karthik, I will tell you in between also that how you can do the hands-on on it. Well, thank you so much for this incredible session so far, sir. The
Okay,
practical
thank you.
examples shared, you have truly helped in simplifying the complex concept and make them more relatable. I hope all participants have not missed this opportunity to note down the key points from the hands-on masterclass session as delivered by sir. So I can see there are a lot of questions from the participants. We will surely be addressing your question shortly. So as part of our commitment to bringing you the best career opportunities, we are thrilled to present an exceptional program launched in collaboration with IIT Hyderabad and TCS Ion. This 2 months live online program with an optional 1 week on campus bootcamp. This is the point which I was talking about, Karthik, that 1 week on campus bootcamp is designed to give you a deep and hands-on understanding of VLSI and chip design, a field that's powering innovation across industries. You can see here, there is a proper course, 2 month certificate program course of IIT Hyderabad that is of 40 plus hours. And then after that, 1 week of dedicated boot camp in the IIT Hyderabad. And you can eligibility is bachelor and master's degree, and individual who is interested to pursue in the research in the field of VLSI, and the potential career paths are VLSI design engineer, physical design engineer, analog design engineer, and many more. And average salary is between 7 to 20 LPA. Next slide, please. Next slide, please. Yes. So here you can see the scan, you can scan the QR code also, and already AV team already posted a link here also. You can directly click on the link and go for the registration. And the important point is that the amount is rupees 14,160 of this course. But if you will take the additional boot camp, that is a hands-on practice. So that is of 9,440. That is your choice. You wanted to choose it or not. The course is of 14,160, and the 1 week boot camp is the additional cost of rupees 9,440. And you can scan this QR code, and link is available in the chat box. So with great respect and excitement, let's hand over the session to the couple sir, who will give us guide us through the remaining part of this insightful journey.
Hi, am I audible?
Yes, sir, you are audible.
Good evening to all. I'm Dr. Kapil Jainwal. I'm from Electrical Engineering, IIT Hyderabad. So we have very great insight given by Dr. Abhishek. He nicely introduced the concept of uh, analog and digital IC design, and what is the importance of digital signal processing or digital circuit design and analog. And of course, because we are living in a world which is analog in nature, the signals which are all coming from the external world, which we need to process in order to gather the information and process it, we need to have analog processing. And of course, everybody wants to have one compute system, or as you can say, one electronics which is very smart in nature, which won't consume any power, ideally, very fast, and can process all sort of signals. Whether the signal is coming from audio frequency, which is the way like what I am speaking and what you are hearing, it is audio frequency signal. Saying is that Dr. Abhishek nicely introduced that, okay, where all the signals which we are receiving from external world is analog in nature, and that is why analog processing is very, very important. And as we are dealing with technology all over, all across, surround means we are surrounded by technology. We need to have very smart systems, and the systems should not be consuming much power. It must be very, very high speed and very compact in nature. So that is why our systems are carrying very miniaturized or small area electronics, and that is why ICs are coming into the picture. So integrated circuits are the, means you can say that they are the electronics, the major of electronics, which are conditioning all sort of signals, not only sensing but processing, not only in analog domain, but becoming the, means these analog blocks are becoming bridge between sensing and digital part, because processing is very easy in digital domain, storage is very easy to be in digital domain, it is very cheap because technology is shrinking down to very fine level of in the range of nanometers. So it means once the signal is in digital, but before that we need to process that thing in analog. Now, I won't repeat the importance of analog. I would like to share my screen and start the very basics, how to design it. What are the basic steps? Analog IC design. And specifically, when we are having some softwares, very professional softwares, what are the basic steps? So my screen is visible to you?
Yes, sir.
Okay. So if I would like to share very basic of an IC, it looks like this. Fine. So over there, you can see there are, means this IC over here is, it's something called the layout of an IC. Means at the top view, you are going to see this diagram which is shown over there. So in this thing, if we further zoom in something, then you will see something which is visible over here in this. Now, this particular thing is, you can say, a zoomed version of an IC. In this thing, lot many different type of blocks are there. Some of the blocks are analog in nature, some of the blocks are digital in nature. But the overall point over here to show this thing is this view is called, this is a physical view of an IC. And we also, while designing the circuits, we not only design the circuit on software, but also in the using software also we can design the layout of it. So in this slide over here, I have showed a very basic diagram of one circuit, which is a very standard circuit, that is an inverter. So the left side, we will be having the schematic of an inverter, means it is symbolic view of an inverter. Whereas the right side, I'm showing you the layout of it. What is the meaning of layout? Means when we are fabricating, or when we need to fabricate this circuit, uh, we need to have a blueprint of the circuit. And in VLSI, specifically when we are saying the chip design, there are basically two parts. One is to design on software, and second part is to fabricate whatever we had designed. So in software we simulate it, and for that we are available with some very fine programs, and those are called, and you might have heard that this software called spice softwares, lt spice, ng spice, h spice. So these are basically the softwares which are simulating you of the design which you are, means whatever the design you are having. And the design could be having basic circuit elements, right from starting of registers, capacitors, some transistors in the form of BJTs, MOSFETs, or any other thing, inductors. But what these softwares are doing, the softwares basically are doing, means the simulation. What is the meaning of that? Means when you are when you are basically connecting these elements in a particular way, every element is having its characteristics, and those characteristics can be defined in terms of modeling, mathematical modeling. So for example, if I'm asking you what is a what defines the, means using Ohm's law, we are having this famous equation of V equal to IR. So if we are applying a certain voltage across a resistor, if the register value is known, you can find out the current across it, right? So this V equal to IR is a mathematical equation through which you can find the value of current across it. Similarly, if we are going with the very complex equations, means in this circuit, if I want to know the current, I want to know the node voltages, if I know the equations which are defining this circuit, I can have all the values. I can solve these equations, and I can actually have the whether the node voltage, node current, the current between two terminals. These are very specific thing, but even we can do more complex analysis like noise analysis, frequency analysis, delay, transient analysis. All these things can be done, but we need to have those equations. And once we are having multiple of equations, we need to solve that thing. It is just like solving a differential equation or higher order equations. So these softwares, basically, what they are doing, the way you have configured your circuit, it is making different equations which are belonging to a node and devices, and solve that equation for all the variables and then give the solution. This is what these softwares are working. These are called EDA tools, or electronic design automated automation tools. The way Dr. Abhishek presented, he was using one very industry standard software that is called CAB, that comes from the company called Cadence, and the device flow was Virtuoso. Similarly, we can also have other softwares which are being used for IC design, which are coming from Synopsys or Mentor Graphics, or some other freewares are also available. So these are softwares. Using these softwares, first we design the circuits using this kind of symbols. This is the schematic we design, and after that we make the blueprint of this device which are going to be fabricated. That is called the layout view, which is at the right side of this particular slide. So when we are designing, of course, we as I told as Professor told you, that analog design is the specification of analog system is not as easy as digital, because in digital we are dealing with only two levels, 1 and 0. Between that thing, if the circuit is getting transient, we are only interested at how fast it is going back over there, and we are interested in the levels. But in an analog, it is not the case. Every single, if the signal is varying between one point to another point, every value has to be processed properly, and there will be a certain output corresponding to each and every value of the signal range. And if we, for example, if the signal has to be a very meager signal has to be amplified in this way, every particular part of the signal has to be amplified in a perfect way. If one part of the signal is getting multiplied with m, also all part of the signal has to be multiplied with the m, then only you are replicating the same signal. And for that, the circuit, whatever the system you are designing, has to work or process in a same way. So your circuit, whatever the system you are making, has to function in a similar way for the entire range, and the entire range could be anything, the amplitude, the frequency. These are the basic elements through which are being used to define a signal. Okay, so this overall property is called the linearity. Okay, so not only the linearity, but the noise performance, the transient performance, frequency analysis, all these signal range, power dissipation, the swing of the signal, all these things are very common and standard specifications for an analog system. Now, apart from the basic of the analog systems, if I would like to tell you how to design a particular analog system. So for example, a very basic analog system is an amplifier. So if you are having a diagram ready for, let's say, circuit ready for analog amplifier, it's a very basic element. I'm basic system I'm designing here. I'm input, some bias voltage, and over there an output. So this is basically showing you one schematic diagram of one amplifier. Very basic. Although if I want to make a practical amplifier, I need to add so many things over there, but it's a very simple way to represent an amplifier. This is your biasing transistor. This is an amplifying transistor. So over here, after designing at the schematic level, you do so many simulation. Or then simulation could be different in nature. First of all, if you want to see if you are varying a signal with respect to the time at the input level, how your signal is varying at the output in time domain. So this kind of analysis is called transient analysis, where you are observing your signals with respect to the time. Similarly, you can observe your signal with respect to the frequency. That is called AC analysis. Similarly, you can observe your signal at voltage level at the input as well as at the voltage level at the output. That can be considered as a DC analysis. Similarly, you can, if you want to find out the noise performance of your system, then you are doing the noise analysis. All these analysis you are doing on this system. And of course, the system analysis, when you're using the simulators, that simulators has to be very advanced, because all these analysis are not very simple in nature, and that needs a lot of mathematical equations to be solved. So for that, specialized softwares are to be used, which are available to us, like Cadence, Synopsys, Mentor Graphics. So we do first of all the simulation at the schematic level. Now, once we are done with the schematic level simulation, we are satisfied that okay, we are getting the performance, then we go for the layout design of it. And the layout looks like this. So this layout will be corresponding to the schematic of whatever has been shown at the left side. So what exactly it is? So when we are designing an IC, you will be having this structure and you're simulating it. But when you are designing a layout is nothing but the blueprint of whatever you have designed at the schematic level. Means you can understand, for example, if somebody wants to design, if you want to draw a painting using different layers. So for example, you are available with something, if you are having one structure like that, where here a window is kept. If you are putting colors over here, then eventually you are available with this type of structure in your painting. That could be more complex also. Similarly, the layout is nothing but this kind of blueprint only. Different layers are there. If you are having the blueprint of all these layers one by one, and you're just filling the layers, eventually what you will be getting is this IC. The way I am speaking is looking very simple, but the way we are designing it is very, very complex. So many rules we need to find, so many analysis, and so many, you can say, the circuit design concept has to be kept in mind when we are designing it. So once the layout is done, which has to be exactly similar to your schematic, once it is done, then we are sending this blueprint to our fabrication labs. You might have heard about this terminology that okay, in Taiwan we are having semiconductor fabrication lab. For example, TSMC is one of them, UMC is one of them. Some of them are in Europe, like Tower Jazz or so. These foundries are basically taking this blueprint and getting means returning us the fabricated IC. Once the IC is available, then you can actually um, characterize it. Characterize it. You putting on a PCB or a breadboard. You embed your IC on that. Apply your signals and see your output. If this IC is performing well enough, then you can use it in various applications. If it is an amplifier IC, you know what are the applications, whether it is an amplifier, whether it is in your mobile phone, or whether it is in your audio systems, or in your sensors. Similarly, you can have signal conditioning in analog like filters. Um, you can use in A to D converters, D to A converters. There are many usage of these ICs. So while we are doing this complex step, right from circuit designing till characterization, there are so many steps are involved for that needs not only device knowledge, that needs circuit knowledge, network analysis, control system also. Then you need to have the understanding when you are putting your circuit in real life. So many real life effects are coming which are governed by physics. So to design an IC, right from using a software till being embedded in a PCB board and used in an application, that needs a lot of steps. So in this course, you will be learning all of them. We have given a very brief about that. I hope we are able to convey some of the concepts. If you are joining this course, then you will be getting lot more exposure and lot many details of the design, whether it is analog design, digital design, programming. Some of the programmings will also be there. So the whole course will be covered to make you learn how to make a product level integrated circuits. Thank you so much. I'll stop here.
A big thank you to both Abhishek sir and Kapil sir for delivering such a wonderful and insightful masterclass on fundamental of analog custom IC design. Your clarity in explanation, real world examples, and step by step guidance truly made this session enriching for all of us. We deeply appreciate the time and effort and knowledge you shared with us today. It's been a privilege to learn from both of you. So I would like to take one audience question, that is Shreya is asking which is more demand in market, digital VLSI or analog VLSI? So Abhishek sir, Kapil sir, any one of you can answer this question. Um,
Am I audible?
yes, sir, you are audible.
So the answer, if you see number of companies working in digital domain and analog domain, see right now semiconductor is in booming state.
Mhm.
You might be knowing that okay, if you go into the share market, you will see the share of Nvidia is at very high high price. Okay, in the last 5-10 years, the share of Nvidia is reaching sky high, right? And why? Because over there they are using compute power. They are having GPUs and they are using in being used in AI. So if I answer your question, then we are dealing into the world which is full of ICs. Not only digital, not only analog, mixed signal ICs are there, full of sensors are there. So if you are skilled engineer, then definitely market, we are short of manpower like anything. That is what I want to say. So whether the volume of digital is more, but analog engineers are also very less and demand is very high. So it's totally up to you in which domain you want to go.
Great, great. Hope Shreya, you will get your answer. So, with this, we come to the end of the session. So, I would like to ask Abhishek sir, Kapil sir, would you like to add anything? Last few words.
Just maybe one more point I will add here from my side.
Okay.
So, as we are seeing, in addition to the standard analog blocks, nowadays this compute has become very important. And this is a special kind of computation these days people are interested. So, that is called as approximate computing. So, a lot of compute is being done for this is especially related to the AI and ML processing. And the moment we want to design ICs or systems which can do this approximate computing, at the same time have to be low power, then you will find that analog circuits actually shine here. So if you try to compare digital and analog, so because of already the legacy region, we have a lot of digital systems. Okay, and then almost all the digital ICs also have some analog blocks. But we are seeing a time when the analog blocks are becoming again, this resurgence is happening for the analog circuits now. So, and maybe in the near future, you will find that the analog ICs may start dominating the compute because of requirement for low power approximate computing.
Great, great, great. Thank you so much. Thank you so much for this wonderful session. So with this, we come to the end of the session. In case if you all have any more doubts, any more questions, you all can always reach out to us, info.tcsionhub@tcs.com. And I want to especially thank you, Abhishek sir and Kapil sir. It's our pleasure to have you with us. The way you explained, the way you summarize everything, it was really awesome. Thank you, audience, for your active participation, and thank you once again for your time and presence. So, I, Shruti Kurana, signing off. Have a pleasant evening.
Thank you.
Thank you.
Thanks to everyone.